Let's take a look at section 9.2, which is on the central limit theorem for sample means. So a lot of these ideas are going to be the same ideas we've been talking about in chapters 7 and 8. The only new thing is we're going to apply them to means instead of population proportions. So the central limit theorem for sample means shows that as long as certain conditions are met, the central limit theorem still applies and assures us that the distribution of sample means will follow an approximately normal distribution, no matter what the shape of the population distribution is. So the conditions that we want to check are the same conditions as they were, like I said, in the previous two chapters. First of all, the samples have to be done randomly, which we can assume means independence. So each observation is collected randomly from the population, and observations are independent of each other, which we usually assume. The sample may be collected with or without replacement. It's got to be a large sample. How large does it have to be? Either the population distribution is normal, so sometimes they'll tell you that the population is normal, and that's good enough to go ahead and apply the central limit theorem. But if you don't know that the population is normal, the sample has to be large enough to have at least 25 observations. So in other words, n has to be greater than or equal to 25. Sometimes they'll just say the population is normal, you're good to go, and it doesn't matter what the size of the sample is. But if they don't tell you that, or it's not a normal population, as long as your sample is at least 25, you should be in good shape. And then the population itself has to be large enough so that if the sample is collected without replacement, then the population must be at least 10 times the sample size. If all three conditions are met, then the sampling distribution for X bar, your sample means, is going to be approximately normal. And actually, hold on, let me give you a different notation here. We'll use the normal notation, remember the capital N, with the mean, same as the population mean, whatever mu is, and then the standard deviation is the standard error formula that we talked about in the previous section. So mu is the population mean, and sigma is the standard deviation of the population. And of course, little n is the sample size. Actually, let me make that little n, so we don't get that confused with big N. So this big N means it's normally distributed, and then the mean is mu, whatever the population mean is, and the standard deviation is sigma divided by the size of the sample size. So visualizing distributions of the sample mean, just to give you kind of an idea visually of what we're talking about. The figure below shows the distribution of in-state tuition and fees for all two-year colleges in the United States for a particular academic year. Note that it is skewed and multimodal. The population is definitely not normal, taking a look at it. So it looks to me like it's right skewed and it's multimodal because you got a few different peaks in the graph. So if we take from that population and we select samples of different sizes and we make a distribution for the means of all those samples, take a look at what we have. So the one on the left here is sample sizes of 30, and the one on the right are sample sizes of 90. So what do you notice about each distribution? First, I hope you notice that they're both approximately normal. Not exactly, not perfect, but approximately normal. And notice that both of them are more than 25, right? So it doesn't matter that it came from a population that wasn't normal. Since the samples themselves are more than 25 or greater than or equal to 25, we're good to go. What happens to the standard error as n gets larger? So what I want you to notice is that this graph here has less spread or less variation horizontally, right? So it's more compact. Everything's a little bit closer to where the mean would be. So as n gets larger, as the standard error, just like it did in the last section, the standard error decreases. Remember, so the standard error decreases, and that's what's indicating that you have less spread in this graph because you have a larger sample size than you do in the one next to it. So let's apply this to an example. According to data from the National Health and Nutrition Exam Survey, the mean weight of 10-year-old boys is 88.3 pounds with a standard deviation of 2.06 pounds. Assume the distribution of weights is normal. And they're talking about, assume the population distribution. I probably should put that in here. The population distribution of weights is normal. So they're telling you the population is normal. Suppose we take a random sample of 30 boys from this population. can we find the approximate probability that the average weight for this sample will be above 89 pounds? All right, so let's note a few things. First of all, what do they tell us in the question? The 88.3 pounds is the mean weight for the population. So we know that mu is 88.3 pounds, and the standard deviation that goes with it, sigma, is 2.06 pounds. So the first part, they're asking us if we can find the probability that our sample of 30 boys the mean for that sample will be above 89 pounds. Note that the sample size n is 30. So regardless of the size or regardless of what the population is doing here, we could go ahead and apply the central limit theorem because the sample size is large enough. And let's be a little more specific. Does the central limit theorem apply? Yes, it does. Well, what can we say? We took a random sample, so the first condition was met. The sample size is large enough, it's larger than 25, and the population of all boys in the United States is certainly going to be more than 10 times our sample size. So yes, the central limit theorem applies. And like I said, they also told you that the population was normal. So even if the other conditions weren't met, if the population is normal, you're good to go ahead and start working with this. So what does this mean? We are working with a normal distribution where the mean is 88.3 and the standard deviation or the standard error is 2.06 divided by the square root of 30. Make sure you see where I'm getting that number from. Remember, our standard error from up here, our standard error, it was on the previous page. Let me go back to it. Right here is given by sigma divided by, and you know what? I just noticed I made a mistake in the notes here. This isn't n, this should have been the square root of n. Please go back and fix that in your notes so you see it. That's the square root of n. So sigma divided by the square root of n is the population standard deviation. I'm sorry, the sampling distribution standard deviation. All right, so let's put all this together for our particular distribution. We're looking for the probability that our sample mean for our boys is going to be greater than, where is it in the question? 89 pounds is what they were looking for. Greater than 89 pounds. So the way we're going to figure this out is we're going to use StatCrunch, and we're going to go back to the normal calculator, the basic normal calculator that we used back in chapter 6. You're going to put in your mean is the 88.3 number, like that. Your standard deviation is this 2.06 divided by the square root of 30, and in decimal form it would be about 0.367. And then you're going to put in the probability that X is greater than or equal to 89 pounds. So for me, from StatCrunch, it looks like I'm getting a value of probability of about 3%. So my probability is about 0.031, or about 3.1%. So part B, it says, suppose we take a random sample of 10 boys from this population. Can we find the approximate probability that the average weight of this sample will be above 89 pounds? So to me, I'd see that number 10 and I would think, well, that's a really small number. Can I still apply the central limit theorem? I'd be a little hesitant to do so. However, I can in this case. Again, it goes back to the fact that they told me that the population was normal. So as long as the population is normal, you can take a sample as small as you want. It doesn't matter. It's still going to follow that normal distribution. So let's write some things down. Yes, since the population, so the population was normal. We specifically told that it was normal. So the size is okay. Size of n, I should say, is okay, even though it's smaller. It's only 10. So the same information applies. We're going to say the distribution is normal with a mean of 88.3 followed by a standard deviation of sigma divided by the square root of, not 30 this time, my sample size is 10. And if we put that into StatCrunch, we're looking for the probability that the sample mean is above 89. And so there's the information. We go to the normal calculator again. We put in our information for the mean and the standard deviation. And this time I'm getting a number right here of about 0.14. So about a 14% likelihood. And notice that the sample size was different, which gave us a different standard error, which is the reason we had to go back and recalculate the probability. So let's look at another example. It says home prices in a certain community have a distribution that is right skewed. So they're specifically telling you this time that the population is right skewed. So keep that in mind. The mean of home prices is $498,000 with a standard deviation of 25,200. So part A says, suppose we take a random sample of 30 homes in the community. What is the probability that the mean of this sample is between 500 and 510,000? So does the central limit theorem apply here? Well, we have to check the three conditions because they told us the population was not normal this time. So the central limit theorem conditions, first we were told that it was a random sample, so we are good to go there. The sample size, n, this time is 30, so that's more than 25, so we are good to go there. And we can assume that the population is at least 10 times the sample size. So yes, the theorem applies. So we know that this distribution, sampling distribution, is going to be normally distributed. The mean is going to be 498,000. That's coming from the population mean that they gave me in the question. And then the standard deviation is going to be the population standard deviation, sigma, 25,200, but divided by the square root of n, which was 30. And so I get a, let's see, if I put it in a stat crunch, this time it's going to be between. I'm looking for the probability that x is between 500,000 and 510,000. So 500,000 and 510,000, or x bar rather. And so if we put that into StatCrunch with the information for the mean and the standard deviation, and remember to click between this time, I get a probability of about 32%. So 0.327 is my solution there. Now part B of the question says, suppose we take a random sample of 10 homes in this community. Can we find out the probability that the mean of the sample is more than 510,000? So the problem here is the sample is too small, considering the fact that we don't have a normally distributed population. So the answer for this is going to be no, since n is small, and I'm out of room here on the paper, and if you want to make a note that because the population, we were told, is not normal, so we cannot proceed unless the central limit theorem conditions are met, which they would not be if you had a sample size of only 10. All right, let's look at the next example. One of these distributions is a population. The other two distributions are approximate sample distributions of the sample means randomly selected from the population. One has a sample size of 10 and the other has a sample size of 25. Match each one. So we have one of these as a population, one comes from a sampling distribution of size 10, and the other comes from a sampling distribution of size 25. So let's use a little bit of process of elimination here. I'm thinking the population is going to be the graph here to the right, the population, just because it's kind of all over the place. It's certainly not normal, and it looks to me like it's multimodal and maybe, I don't know, maybe skewed. It's just a mess. It's definitely not normal. So that has to be our population. And then our sampling distribution, we've got one where n is 10 and one where n is 25. So remember, the higher the n, the larger your sample, the smaller the standard error, which means the smaller the spread. So between the two graphs remaining, which one has less spread or smaller standard deviation if you were to look at standard error, really, if you were to look at it that way? I would say this one has less spread between the two. You've got more values clustered towards the center. You've got a higher peak than you do here. They're both, I would say, relatively normal in terms of the shape, but this one's definitely got less spread. So this one has to have the larger sample size. So this one would be the one where n equals 25, and then this one would be where n equals 10. All right, let's take a look at another example. According to one very large study done in the U.S., the mean resting pulse rate of adult women is about 74 beats per minute. So let's write some stuff down. So mu, we know right off the bat, mu equals 74, and the standard deviation is 13. The distribution of resting pulse rates is known to be skewed right. Okay, suppose we take a random sample of 36 women from this population. What is the probability that the average pulse rate for this sample will be 71 below 71 or above 77. So in other words, what is the probability that it will be more than 3 beats per minute away from the population mean of 74? Okay, so we know that even though it's skewed right for the population, we're okay because n is 36. So that means we can use a normal distribution. The mean for the sampling distribution is going to be the mean for the population, which is 74. The standard deviation for the sampling distribution is going to be 13 divided by the square root of 36. And so we're looking for the probability that the mean for my sample of 36 women is going to be below 71 or is going to be greater than 77. So when I put this into StatCrunch, I'm going to use the normal distribution calculator again, but remember, you're in this case, we're looking for two different things. We're looking for the probability that we are below 71 or greater than 77. So if you think about it visually, we're looking for this probability or this probability. There's two ways we could do this. One way would be to actually have StatCrunch calculate the first probability and then calculate the second probability and add those numbers together. The other way to do this would be to find the probability of the in-between area, and then what I'm interested in, the red area, would be the complement, right? So what I'm going to do in StatCrunch is I'm going to click on between, and I apologize I don't have a picture of this, but if you have StatCrunch open, go ahead and go through it with me. Put in the information for your mean and your standard deviation, and then figure out the probability of being in between, so this blue area right here. So for me, I'm getting about 83%. So I'm getting 1, let's see, I'll write this here, 1 minus 0.8338, which would give me, so that would give me about 0.1662, so about 16%. So the second part of this question says, can you find the probability that a single adult woman, randomly selected from the population, will have a resting pulse rate that's more than 3 beats away from the mean value? So the difference here, these questions sound very similar, but the difference is that in the previous question, we were looking the mean of our sample, the probability of the mean for our sample being a certain number. This question, they're just saying if we randomly select someone from the entire population. And the problem is we don't know enough about the probability distribution for the population. In fact, we were specifically told that the population was skewed right. We don't know that the population is normally distributed or anything like that. So no, because we can just say the population is right skewed. That would be sufficient. All right, so make sure you see the differences between those two questions because they sound similar, but you're talking about a different group. All right, the next question. Maryland has one of the highest per capita incomes in the U.S. with an average income of $75,847. Suppose the standard deviation is 32,000 and the distribution of incomes is right skewed, as incomes often are. A random sample of 100 Maryland residents is taken. Is the sample large enough to use the central limit theorem? Yes. Since n is greater than or equal to 25. N is 100, so we're good to go. What is the mean and the standard error? So, of course, the mean is going to be the same as that for the populations, the 75,000. The standard error is going to be sigma divided by the square root of n. So for us, it's going to be 32,000 divided by square root of 100. Square root of 100, of course, is 10, so that's going to leave me with 3,200 for my standard error. Part C says, what is the probability that the sample mean will be more than $3,200 away from the population mean? So we can use StatCrunch to figure this out. Another way we can do this, though, because we're talking about $3,200, and $3,200 is the standard error. So if the mean in the middle, the 75,847 is what we expect, 3,200 away, think about that. That would be one standard deviation below the mean. You can even think of it in terms of z-scores. Let's do that. One standard deviation below the mean and one standard deviation above the mean. And they want to know the probability that your sample mean will be more than 3,200, one standard deviation or one standard error away from the population mean. So they're looking at this probability down here combined with this probability here. So because this is normally distributed, the central limit theorem, of course, we know applies. We can still use the empirical rule, right? We can still use the empirical rule. So recall that with the empirical rule, 68% of the data, remember, falls within one standard deviation or standard error of the mean. So what I'm looking for really is the complement of that. So I'm looking for 100 minus the 68%. Which leaves me with a 32% probability that my sample mean will be outside of one standard error from the population mean. So either 3,200 below the mean or 3,200 or above. All right, last thing I want to talk about is something called the t-statistic. So hypothesis tests and confidence intervals, we use those earlier in the course to estimate the population proportion. Now we can use them to estimate the population mean, or to test the mean according to some hypothesis. And they're going to follow a distribution now that's called a t-statistic. So this is what we would use when we don't know the population standard deviation, sigma. So a lot of times we don't know the population standard deviation. We may have an estimate on the mean, but we don't necessarily know what the standard deviation is. So this will create what's called a t-distribution for us. And we're going to use this more in the next section, but I just kind of want to get you introduced to it. The test statistic that we would use to calculate a particular sample to see how unusual that sample is, we're going to use x bar minus mu divided by the standard error, but the standard error we're going to use S, the sample standard deviation, divided by the square root of n, because again, we don't know what sigma is. So it says, since the population standard deviation is almost always unknown, we divide by an estimate of that standard error using S instead of sigma. That's the real difference here. The t-statistic does not follow a normal distribution, so this is a little bit different. It's a different distribution entirely, and we're going to use StatCrunch to help us figure out probabilities about it, but it's a different distribution. The reason it doesn't follow a normal distribution is because the denominator will change according to whatever your sample size is, so it's not going to always follow that normal distribution that we're used to. The t-statistic is generally more variable than the z-statistic. So back when we talked about normal distribution and we worked with a z-score, we were talking about the z-statistic. The t-statistic always has a lot more variability to it than the z-statistic did. If the conditions for the central limit theorem hold, then the t-statistic follows what's called a t-distribution, and that's what we're going to work with most of the time. A couple final characteristics about the shape of the t-distribution. It's symmetric and often bell-shaped. It has tails that are thicker than the normal distribution, so they come up a little bit higher in the ends than the normal distribution does. Its shape depends on what's called the degrees of freedom. So degrees of freedom, and oftentimes we use df, the little lowercase df, to signify degrees of freedom. If df is small, then the tails are thick. So in other words, as the degrees of freedom increases, the tails will get thinner. And as the degrees of freedom approach infinity, the t-distribution approaches the standard normal distribution. And like I said, we'll see a little bit more with this in the next section, but I just wanted to introduce you to it here.